Okay, so the spaces we'll consider which are important from the fundamental group point of view are two complexes. These are the result of attaching two cells to a graph. Okay, so we can take attach 0 cells to an empty set, then 1 cells, and then 2 cells. We'll remark what happens when you attach 3 cells, but this is the important case as far as fundamental groups is concerned. So these are given by, well, I have a gamma, okay, and pi1 of x comma, not x, well, okay, x is mod gamma. Okay, by the way, this is usually denoted x1, one skeleton, one dimension. This is the free group. Okay, and we have phi alpha mapping s1 to pi1 of x1. Let me stick to this notation, x0. Okay, so the class of phi alpha is not defined in so phi alpha is not defined in pi1 of x0, but is instead defined in pi1 of x1 and phi alpha of 1. Okay, but this is well defined. This gives you a well defined conjugacy class in pi1 of x1 phi alpha. Not phi alpha 1. The whole point is with the given base point. Okay, so this is the general principle. We have seen that if I have a loop which is somewhere else, I have a change of base point map which will send it to x0. But that depends on the choice of path. But if I chose a different path, I'll get a conjugate element. Okay, so we'll regard these as, so up to conjugacy this is well defined. Okay, so let me say, let's just give them some names. Let R alpha be representatives of these conjugacy classes of these. So we have elements in pi1 of x1, x0. They're dependent on R alpha. R alpha doesn't depend on the map, but up to conjugacy it does. It depends on map plus arbitrary choices. Okay, so now is the theorem which follows from Van Kampen theorem, and a little care with base point which I'll omit. That is that pi1 of x, so let's call this x. Okay, so given by gamma, so x result of attaching two cells. So pi1 of x, x0 is going to be equal to the free group generated by, well, whatever it is, but for now let's just call it pi1 of x, x0, quotiented out by the normal subgroup generated by R alpha, alpha in S, not in S now, alpha in the quantity A. So this is the normal subgroup generated by that. Proof is by Van Kampen theorem. Okay, and let's just look at some pictures. I'm going to ignore fiddly base point issues. But what is our space? We start with a graph. Okay, and so let's take a neighborhood of this as one of our sets in the Van Kampen theorem. So I'm taking this as neighborhood of x1. Okay, a graph may be more complicated than that. And then I'm attaching two cells. One of them, another of them. Let's say I attach two cells using some maps onto the graph. Okay, so what happens if I take so I take a neighborhood of the graph, so it will involve a little annulus around each two cell, and I'll take the interiors of two cells. Okay, so using let's say neighborhood of x1 and interior of two cells, plus some little twiddling for base point. Okay, and so what happens in this case? What is the fundamental group? So we get pi1 of the neighborhood of the graph, x1 star, x1 with base point x0, and we have all alpha in A of the fundamental group of the disk. And what is the fundamental group of the disk? Trivial group. So you take free products of trivial groups, you're trivial, and you take the free product, it is this. divided by the relation. And what is the relation? Relation tells you that any element, so let me draw the disk a little larger, and here is the annulus. So the intersection is this one, okay, allowing for some tweaking for base points. It tells you that any element in this fundamental group, okay, if I look at its image on the boundary, which is in x1, okay, by perturbing base point, I mean by connecting to the base point and so on, that is exactly these elements R alpha, okay. And what about its image in the disk? It's trivial, okay. So this is divided by the normal subgroup generated by R alpha times E inverse, if you wish, which is what you have as this claim, okay. So what we have here is that the fundamental group is this space given by these, okay. So we'll introduce a little bit of notation and make an immediate corollary to this. Okay, so suppose we have S. So suppose we know pi 1 of x1 and x0 is the free group generated by S. We'll know it's a free group. S is as we had described before, and R is some set. So R is simply a subset of elements in S. Okay, so these are words in S union S bar. That's a slight abuse because different words can give you the same element if they are not reduced words, but essentially this is there. So we say definition, the group S divided by the normal subgroup R is the group with presentation S given R. So what we have seen is, given a 2 complex, we get a presentation of the fundamental group, and if it involved only finitely many cells, we would actually get only get a finite presentation. Okay. So example, in fact, Z squared is the group with presentation alpha beta. Okay. So this is written this way, or it's more often written this way, S semicolon R. I'd prefer that notation. Let me write it this way. Semicolon alpha bar beta bar. So if I look at alpha and beta, the free group generated by that, and add the relation that they commute, what I get is Z squared. This is the free group. Okay. So easy fact is the following proposition: every group has a presentation. And how is this the case? As I said, it's easy if you are willing to be gross. Any group is generated by all its elements, so it's always generated by a free group. So you have a surjection from a free group. The kernel is some normal subgroup, and that's generated, for example, normally generated by all its elements. So take those as the relation. Okay. More interesting is whether you have finite presentations. Many nice groups do, many others don't, and sometimes this can be a subtle question, but every group has a presentation. And as a corollary, we get the following theorem: if G is a group, there exists XX0, and this is in fact a 2 complex such that G is pi 1 of XX0. 2 complex is something obtained by attaching 0 cells, 1 cells, and 2 cells. Okay, let me write there exists a little better here, because that looks like an operation there. So there exists a based 2 complex. It's just connected, in fact. It's path connected and has all nice properties, with G being the fundamental group. Why is that? Because I take generators, I take a presentation, I take generators. Okay, so let G equals S semicolon R. Okay, take this graph, what we had earlier. Okay, so that is to take one 0 cell. Last time I had said vertex, one edge. Oh, these are called cells, by the way, that we attach. So one edge, that is 1 cell for each S in S. And then for each R in R, you attach a 2 cell. So we have lots of fundamental groups. Okay, so this is very nice. It gives us lots of fundamental groups. The last thing we'll see in this part of the course is that some of our familiar spaces, in particular surfaces, have such a description, and hence we know their fundamental group as well.